everyone. I'm hoping that you all have Docker set up and the day one image downloaded and set up as well. Again, in case you have any issues, please raise your hand and some of our volunteers will help you out. For 5 more minutes, maybe, I don't know. Yeah, and if anybody has an issue, just let me know, otherwise we'll go ahead. Thing we call the dispersion constant. I think this is one of the most major disagreements, even more major than the Hubble tension in pulsar and FRB astronomy. Nobody agrees on what the value should be. People have written papers on what the actual value should be. This is from one of those papers by Shri Kulkarni. He recommended to use, this exact value, but you can use whatever at this point. Yeah, so this is what that looks like. This is a pulse from BO329 plus 54, very bright pulsar. You can see this burst in example 00.fill, which you should have if you have the Google Drive on your systems. It's just this burst cutout. It's a particularly bright burst that we got. You can play around with this. You can see if you can plot this by yourself. There should be a prelim.ip, a prelim notebook, a Jupyter notebook in extras, the extras directory. So you can give it a go. If you're not familiar with the SIGPROC filter bank format, you can see how to open the file and plot the data. But again, it's extra, so feel free to try it on your own time. Okay. So we need to correct for this effect of dispersion in our data. Otherwise, we can't search for bursts. So this process is called de-dispersion. And so there are two types. I won't be going into why there are two types and what they do, but essentially we use incoherent de-dispersion when we are searching for bursts because the other one is computationally very expensive. And so what we do is we correct for the delay in each frequency channel, and then we just add things up. So, but the problem is we don't know the DM beforehand, so we have to do this for a lot of DMs. This is called a DM search. And so, again, thanks to Kaustubh for sharing this graphic. This shows that if you de-disperse the time series at different DMs, what happens. And as you can see, as soon as we reach the correct DM, the burst peaks, and otherwise it gets smeared out. And so the hope is that we will do a search over a lot of DM trials, over a very large DM range, and the burst will show up at the correct DM. So then we get a time series from each of them. The original data we had was a frequency time array of intensities. When we de-dispersed it, we collapsed all the frequency channels after correcting for the delays in each channel. That gave us a time series for each DM. And so then we do a single pulse search. We search literally for individual pulses in each of those time series. And the way we do that is by using match filtering. We have not really changed this technique since 2004 or 6, when I think Mora and Jim came up with it. And essentially what we do is we convolve a time series with a boxcar. So basically match filtering comes from a theorem by the same name, which just says that if you convolve a signal with something which is similar, the signal to noise ratio will just maximize, otherwise it won't. And so in this case, the boxcar doesn't really match our signal, but convolution with a boxcar is very cheap because it's just a cumulative sum of all of your samples. And so you would do a convolution with a boxcar, you get a maximum SNR if the width of the boxcar matches the width of your pulse. So what that tells us is you will get a time of arrival where the SNR peaks, obviously. But because you're trying multiple boxcars with different widths, you'll also get an optimum width for your burst, right? And so after single pulse search, you get a long list of candidates, which has a DM value, an arrival time, a width, and an SNR, a signal to noise ratio for each candidate, right? And I think one of the major jobs of FRB astronomers is to go through all of these lists and find bursts, right? And so unfortunately, these are too many most of the time. We have had instances where these can go up to tens of thousands, millions, depending on our RFI situation and so on. And so we do something called clustering. We do this. So again, there is some slight change here. So if you are using the Presto containers, which I will come to later, you are not doing this, unfortunately. But if you are using the original containers for today, then we are doing clustering via dbScan. So dbScan is a density-based clustering algorithm. And so what it does is essentially that you need to get rid of spurious candidates. So what the main reason for spurious candidates is that the same candidate will come up at a lot of different DM and width values, because as long as the SNR of your candidate is above a particular threshold, it will show up. So even if your DM is slightly wrong or the width of your boxcar is slightly wrong, if your SNR is say greater than 7 or greater than 10, which are typical values of thresholds that we use, that candidate will show up at multiple places in your list of candidates. And so now that is essentially the same burst. And you would want that to show up once. And so what you do is you cluster it this way, pick out the burst instance of that burst where it was detected with the maximum SNR, and regard that DM and width as the true DM and width of that burst. Does that make sense to all of you, I hope? Yeah, so feel free to stop me for questions. Yeah, so basically what dbScan does, it selects random points and it picks out a neighborhood of that point. And then if whatever points are within the neighborhood become a part of that cluster. If the number of points is less than a threshold that you have defined, it won't consider them to be part of a cluster, otherwise it will. And I hope this GIF shows how dbScan works. I just pause for a few minutes so that the GIF can get going. So it picked a neighborhood. There were more than 4 or more than 4 points. It made them part of the cluster. And again, it got more than 4 points. They became part of the cluster and so on. Now that point was ignored because there was only 1 point within the cluster, so it got ignored. And similarly, the 2 very small clusters will get ignored as well. They will be treated as noise because we have defined a minimum threshold of 4 points. And so that way will form 2 large clusters and the rest will go away. So that's how we will remove a lot of spurious candidates, because this entire thing will essentially show up as one burst. And typically we do this in the DM and arrival time plane. So a lot of bursts with the same burst with a lot of different DMs will become one burst at one particular true DM of that burst. At least that's the hope. Okay, so I hope you got all of that. If you didn't, feel free to ask questions. As many as you want. And I hope you've already tried this. So to get the actual container going, you have to do an enter.sh. You have to run that script. The image will get downloaded automatically. I'm pretty sure you have all set it up already, right? For some of the my bad. So for some of the Mac users, you have to try a different container. And I think you have already set up that as well. So should be fine. So yeah. So this is the main command. So what this does is TransientX is the software that we are using to do most of the FRB search. And what this will do is it will de-disperse the data at a series of DM values. There is a de-dispersion plan defined. I'll see if I can. Yeah, so okay, so this will basically just tell TransientX not to downsample in time. The sampling time is already low, and not to downsample in frequency as well. And we have set a threshold of 7. So any burst with an SNR greater than 7 will show up in your search. And then it will use a ddplan.txt. It should be there in your data directories. So that defines the de-dispersion plan. So what we do is we divide our entire DM range, which is 0 to 1000 for our tutorial, into small DM ranges and define custom DM steps for each range, mostly so that we don't miss any burst because of the smearing caused by dispersion, right? So we have to define an entire de-dispersion plan to ensure that we detect these bursts optimally without missing them because of dispersion. And so that's what the ddplan.txt will do. And this should give you basically a series, a lot of time series. But what TransientX does internally is make a 2D array where each row is one of the time series at a different DM. And that becomes something called a DM transform. I'll show what that looks like to give you an intuitive idea. And of course, this is the file that you will be using, example01.fill. Okay. Yeah, so for details about the other options, feel free to see the help of the command. Hopefully that decodes it a little bit. Yeah, unfortunately for those on Mac who have M1, M2, M3, M4 chips, Transient X simply does not work. So you can do the same thing, generate a series of time series at different DMs using Presto. You should have an enter presto.sh command, which will enter you into a container where Presto is installed. You can run prep subband with a low DM of 0, a high DM of 2, if I'm not wrong, I think 1000 or 2000 in this case. And I've set a wide DM step. I'm hoping it is fine. And then you can do the same thing. You can give it the same file. And after that, you can run a single Perl search via single Perl search.py with the same threshold of 7 and see if you get the correct output. So you should detect a few bursts from this file, and then you will see how it goes. Right? You should have a tutorial.pdf in your Google Drive folder, has the same instructions. So you can look up the instructions from there. You may not need to look at the slides themselves, but I'll still leave the instruction up there so that you can all give it a go and see how it goes. Yeah, you should see something like this eventually after searching. So you can think about some of these things, right? After you get the burst, right? So first you can run the command, get all of these PNG files. You should have a lot of PNG files dumped into your data directory after you run the transient X command. Some of the files should look like this. Hopefully one of your files looks like this at least. And then you should think about some of these questions, whether it's pulsar or an FRB, how do you verify, what type of source it is, so on and so forth. But again, we'll come back to this in 10 minutes. The question that was asked was, how do you decide the de-dispersion plan? How do you make the de-dispersion plan? Basically, you have parameters for your survey. You know which telescope you're going to use, which frequencies you're going to plan to look at the sky. And so according to that, you have some idea of the dispersion smearing. So basically, you know that if you get the DM of a burst wrong by a particular value, say by 0.1 parsec per centimeter cube or something, it will get smeared away. Or maybe after 0.5, it will get smeared away. So accordingly, for each particular range of DMs, you have to design an optimum DM step so that if you get the DM wrong by a particular amount, it doesn't get smeared away. And so you capture it in the next DM try. So if the actual DM was 100 and you went to 99, you should get the burst. If you went to 99 and the burst disappears below your threshold, then it's a problem. So you accordingly have to decide your DM steps that way and design a particular de-dispersion plan that way. So yeah. Yeah, this will take time. Let it happen. So I'm essentially going through the tutorial with you. So I'm just pulling up the Docker image that we made for day one. Hopefully, as soon as this gets pulled and I enter into a container, I can run the same steps as you guys, and then we can go through it together.
On the Google Drive link be one more file, which is a Python code to convert your dot single pulse files to a single CSV file. You can that code. You have to use that code, and once you have run this single pulse, you get something called as dot single pulse files, and that we will be using for the next steps. So to convert that into a single CSV file, a code is available on the Google Drive link. Please download that and use it. Yes, yes. First, at least do that. Once the single pulse file is converted to CSV file, we'll tell you the next steps. This is only for the Mac users. Hello. If anyone is having any doubt, please ask us for the Mac working.
I will take some time. What I will do. क्षितिज क्षितिज क्षितिज
हाँ
अरे नीचे
अच्छा नीचे
हाँ
Hello, for the Mac users, there is this the Docker that we are using, Presto Docker, which it will be only used for single pulse search. That's it. Any other processes will you have to shift to the this enter.sh Docker. That will be the Presto is only used for single pulses. All other processes will be done on the original Docker, which was shared earlier.
This has been processed and de-dispersed at the particular DM of the burst. This thing is called a DM transform. So essentially, we talked about how we have a time series for each DM value. So what we essentially do is stack all of those time series, which are essentially 1D arrays, and those become a 2D array with y-axis will be the DM, and the x-axis would be time. And that's essentially what a DM transform is. So you just stack all of the time series at different DMs to form the DM transform. And that should have essentially what we call a bow tie-like pattern. So I don't think, so you can see a kind of a cross here, which peaks at a particular DM value, which tells us it's an actual astrophysical source. If it looks horrible in any way, then that means that that is not an astrophysical source because it does not have a particular DM because it comes from Earth, not from space. So it didn't travel through any ionized plasma, so it does not have any DM, right? That makes sense. That makes sense, right? Yeah. So, again, this plot collapsed along frequency. This plot is just, again, this plot collapsed along time. So we call this the band pass, and we call this the de-dispersed pulse profile, right? A lot of the details about the burst is here. So the RA deck, other details. Yeah, can here.
The spectrum on the right side does not look like actually the spectrum of the dynamic spectrum.
Yeah, so that's one reason for that could be because it's integrated in time. So it lost some of the information. So if I only took the spectrum from this particular chunk of time, it might resemble the spectrum of the FRB more. But if I collapse the entire thing, it might not. Because there could be, because of the noise, things can get a bit weird.
Even if you consider the noise, it still does not look like
I know.
very much
Yeah.
of an integrated.
Yeah, I am also a bit unsure why. Ideally, I would have expected it to fall at high frequency.
Like
but
cumulatively added things, but there are
So it looks like cumulative sum, but it's actually not cumulative because there are other candidates in which the profile falls.
which is good, right?
I
don't know. Yeah,
Yeah.
I would expect it summing the entire thing,
Huh.
but again, it's not summing up a lot. But
Yeah.
yeah, ideally it should not have that much of an effect. But I'm a bit unsure. One thing could be that it's there are some RFI or something, or there are just generally high values there,
That
which could
is
cause it to not fall, but not sure.
Yeah, I mean that is fine that in the terminal channels like initial and final channels there it's problematic, but even in between it looks weird. So I'm not sure what exactly it
because
is.
the peak should be somewhere around
Yeah,
here
yeah.
from the eye, but
Because the noise more or less looks uniform. It does not have that trend that is
yeah,
showing.
I don't think the data itself is problematic. So maybe something else is going wrong. I'm not sure. But again, yeah, it's a good question. No, sorry, is it a chi-square plot? No, it's an integral flux. No, it's written right there. The y-axis is integral flux. If it were a chi-square plot, I would maybe that would explain it, but I don't think so. Yeah, it's an integral flux plot. So I think it's all it's done. They have just collapsed this. Just it's an integral flux. It's just a band. Should be a band pass, but I'm not sure what's going on. And that's also this is flux. It's written right there. So that I'm sure. But it's written integral flux, but I'm not sure what's going on. Yeah. Yeah, I don't know. Yeah, 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 could be, but again, it's written, the plot is labeled as integral flux. Yeah, who knows? Maybe it's a bug. I don't know. I'm not going to speculate. Yeah. Sorry. Yeah. This is, I think, Yanpeng Men from the Trapham collaboration wrote this. So the idea there was that he wrote Pulsar X and Transient X for the Trapham survey. They were, if I'm not wrong, doing targeted searches for pulsars in globular clusters using Meerkat and its multiple beams at the time. And so all of the softwares are optimized for that survey. Pulsar X and Transient X are optimized for that survey. So Yanpeng Men, Yunpeng, Yanpeng Men, Men. Yeah, it's a Chinese name. I'm probably mispronouncing it. My apologies to Yanpeng. Okay, yeah. Okay. Yeah, no, okay. I think we decoded okay. So this is literally the cumulative flux integrated across frequency. That's why it's peaks at the end. It literally sums up the flux cumulatively sums up the flux along frequency.
But that cannot be the case because I can see at least one candidate in which the sum is falling.
That is odd, right? A cumulative sum cannot fall.
Exactly. So that's why it cannot be the cumulative sum.
Flux is negative. That's not possible, right? Which file? I think I need to ask. I think both of those files should not be normalized. I'm quite sure, but yeah. So is this example 02.fill, Kenil? One? Oh no, that should not have any. I don't think so. Yeah, I'm quite sure it should not have any problem with normalization. I didn't do anything. It's raw data from the telescope. Yeah.
Yeah. So what Pulsar X or Transient X does, the first step it does is
If it
divides
normalizes
it by
and then calculates the.
yeah.
That would be.
That's the first step that's done, and then they imagine everything to have zero mean and one standard deviation.
That is possible. The flux values will be. That would be a bit silly, I feel. But it should calculate the cumulative flux before
No, it's for RFI candidate. It becomes like this.
Yeah,
It's
okay.
how it is.
Then it makes sense because if it normalized and then did a cumulative sum, that cumulative sum might fall if they are negative values. Again, a bit silly, but that probably explains it, I think. Example one, right? Yes, yeah, it does have multiple bursts. I don't want to say how many until people, yes. Yeah, yeah, we'll see how many people will detect. Yeah. Hopefully, if you have the plots, for example, one.fill, hopefully you have started thinking about some of these questions, whether it's a pulsar, whether it's an FRB, whether it's some other source. And hopefully you have also started to think about how you can find this out. Right? I will discuss this a bit more, hopefully when more people have the outputs, but once you have the output, do start thinking about these questions as in given the information you have from the transient X or Presto outputs, can you find out which source it is? Don't answer the question. Think about it.
I'm asking a question. I want to ask a question.
Oh, sure. Go ahead.
I cannot see where to search for the array deck and like in the FRB catalog.
And just give me 5 minutes. We will share resources for some of the programs that you can use. Yeah. If some of you have tried to run your CAN maker by any chance, so your CAN maker runs on the CPU because again, we don't have GPUs on your laptops, right? So it will run very slowly. So I would advise that you either don't run it for very long or don't run it at all. There are H5 files, hopefully in a H5 files directory inside the data directory. So you should be able to try fetch on those and get some feel for how that goes, right? And you can plot those H5 files as well. I will see if I can share a command which you can use to plot. And then you can have a look at the plots as well to see what the features look like and what fetch does. I will come to some of those things in a bit. We have a Google Doc which has a lot of Pulsar FR related software. So I mentioned some of those questions, right? So you can use some of this software to maybe answer those questions. Plus it's a good resource to have anyways, because it's a good list of Pulsar and FRB software in general that we use. The stuff related to feature extraction and classification, basically why we use AI and so on, that will be done after lunch. So we'll pick up some of that part of the tutorial after lunch.